Okay, we are back, and now we are continuing again in chapter 6. Okay. Isomorphism. And now we're moving on, though, to automorphism. Okay. And the definition is, and again, I'll stop saying it, but you all know when you need to pause it and write everything down and come back, you can. All right, so isomorphism from a group G onto itself is an automorphism. Okay, so you still have the three properties you need to check: one-to-one, onto, and the homomorphism property. But now we're saying we're being very specific. So it's a subset of our broad definition of isomorphism, right? Because it's from G onto itself. All right, and so just a couple examples. Phi, if we're going from the complex to the complex numbers, given by phi of A plus BI, which equals A minus BI, which you should know is the conjugate, right? This is an automorphism of the group of complex numbers under addition. I put this in my notes way before, but I think it might be a good one to do. So maybe on Tuesday for our board work, I'll have someone present that. So yeah, try to complete that one before class. And then phi from C star to C star is an automorphism under multiplication. Okay, C star, as we know, represents all the complex numbers except for 0. Okay. All right, C. So phi of AB, and going from R2 to R2, right? So we're looking at an ordered pair here, given by phi of AB equals BA, right? So we just flip those two entries, is an automorphism of the group R2 under component-wise addition. Now, as you can see, the steps are already written out, and I did that because one-to-one, onto, and even the homomorphism property, although we haven't been doing that as long, should be familiar to you all. It's given here, so if you want to stop and not look at this and then try it on your own and compare, and I'm going to do the proof of one-to-one, onto, and the homomorphism property for this problem. I want you all to become comfortable with dealing with ordered pairs. I think on one of our exams we had, there was a little confusion when it was like in R3 or something, but the structure holds the same. So remember, because we're trying to, for one-to-one, right, we're saying take any element in R2, right, and then phi of take two elements in R2 in the domain, right? So in this case, it'll be ordered pairs. So x sub 1, if phi of x sub 1 equals phi of y sub 1, then x1 equals x2 and y1 equals y2, because we're looking at this from component wise. So we know what that means in terms of being equal. All right, so that's what we have to show. So let's assume that x1 and y1 and x2 and y2 belong to R2. All right, so I'm just taking two elements, and I'm not for sure why that is there, so you can just omit that. Suppose, all right, well, this show part really sets it up for you, right? So suppose phi of x sub 1, y sub 1 equals phi of x sub 2, y sub 2. Well, by the definition of what we said, by the operation, what's going on, we flip the two, we invert them, so y sub 1, x sub 1 equals y sub 2, x sub 2. But by definitions of ordered pairs, that means that y sub 1 equals y sub 2 and x sub 1 equals x sub 2, and therefore it is one-to-one. Okay, so we're going to go into onto. So if you want to pause and try to do onto on your own and then come back, that's fine. Okay, we're back. And onto, it's not too long. Here, remember, and if you want to make sort of onto your notation in regards to, here I'm talking about the codomain, right? And here I'm talking about the domain. We know they're the same because we're trying to prove that they're automorphisms. So the domain and codomain will be the same. Okay. But in terms of onto, if you want that clearer structure, you can. So because onto is saying for anything in your codomain, right? There is an element in your domain such that phi of that element equals whatever's in your codomain. Okay. And so here there exists a PQ such that phi of PQ equals XZ. That's what we're trying to show. So you sort of should know already what to make your P and Q. Remember from proofs, when we have a proof involving and there exists, we have to bring it out, right? For all, we keep it in general, but for there exists, we bring whatever that is out. All right, so here's our proof. Let XZ belong in R2 and let PQ belong in R2, such that, all right, because again, XZ is a for all, so we keep it general. But this exists, so we have to state exactly what we're saying it exists. So P equals Z and Q equals X. Okay. Hope you understand why that's the case. And then phi of PQ equals phi of ZX if we substitute in our values. And by our definition of our phi, that equals XZ. Okay. Therefore, it's on to. All right. Moving on to the homomorphism property. All right. And I hope you can see that yellow is kind of light. The homomorphism property, again, that's there to help us. Some issues with my stylus. But the homomorphism property is there to help us preserve, to see if our binary operations are preserved, right? Because whatever operation is going on in your domain, it could technically, in general, could be different from what's going on in your codomain, right? And so the homomorphism property is to see if structure is preserved. All right. And that's the main reason. So the setup, so we have to show that if we take, and of course, because we're doing an automorphism, right, the operations will be the same, right? But we have to show that phi of, if we take two elements and add them together first, that will equal, well, in this case, because we're looking at component-wise addition, we want to know if that's going to equal each individual element being added. Okay, see the difference from that? All right, so let's see. Let x1, y1, and x2, y2 belong to R2. So phi of x1, y1 plus x2, y2. So this is all together, right? Well, we can bring them together because we're looking at component-wise addition and say that equals phi of x1 plus x2 and y1 plus y2. By our operation, what happens, it equals y1 plus y2, comma, x1 plus x2. Also, phi of, so let me stop here, I'm sorry. What we have done before is, well, from this side, we usually go straight to conclude this right here, right? That's what we're trying to, actually, no, I'm sorry, I put it backwards. We're trying to conclude this right here, right? But this is different. And it's different because if we were to stop, so let's say we are just looking here, all right? If we're just looking here from the left-hand side, is it necessarily clear to us that we're going to end up here? If it is, then we can go ahead and conclude it and we're done. But if it's not, and sometimes it may not be as clear, or maybe you have to finagle some more work, I don't know. But if it's not clear and you sort of get stuck in wanting to show that it equals that right-hand side, then something you can do, and you can do this with induction as well. It works with induction proofs. If you get stuck on the left-hand side, work on the right-hand side, and somewhere along the lines, if you show that those two sides are equal, then you're done, right? And so that's sort of what I did here. I wanted to show you this because I wasn't, I'm not clear. It's not as clear, I should say, that this is going to equal that. If I were to label this, that A truly equals B, okay? And so because I'm not clear on that, I want to look at the right-hand side. So now I went to the right-hand side to play around with that side to see, well, maybe some kind of way I can show that it equals some part on the left-hand side, right? And in fact, I can. So that's what I did. So I took them separately, phi of x1, y1 plus phi of x2, y2, and that gives us y1, x1 plus y2, x2, using component-wise addition. That's y1 plus y2, comma, x1 plus x2. And what do you know? That equals the left-hand side that we started with originally, right? And so therefore, phi is automorphism under the given operation in R2. Okay, hopefully that made sense. I'm stopping this video and then we have a little more to cover and we'll be done with chapter 6.